Alright, chat. Is it working? It better be working. It better be working. I hope it is working. Alright, let me check my live stream. Okay, copy that and then share this link to my Twitter and a bunch of Discord servers that I'm in. And yeah, shamelessly plug my live stream. All right. How have you guys been? Give me a sec. How have you guys been? I've been playing a little too much Silk Song recently. Within like a week, I think I sunk in like homework stream. Yep, welcome Flux, welcome to the stream. Here we go again. Another homework stream. I've been playing a little too much Silk Song. That I wasn't really doing any of my homework. So now I have to catch up on it a little bit. In fact, one of the homework here is due today. So that's fun. That's fun. Why is my Discord not showing streamer mode? How do I make it show streamer mode? Streaming homework. Streaming my homework. Put that there. Alright. Alright, which channels? Where do nerds live? Which Discord server do nerds live? And whatever. We'll be fine. Yeah. Okay, so let's just get right into it. There's a bunch of homework that has to be done. Namely, we have this thing right here. Wait, what? Namely, we have this thing right here. The differential equation that we have to solve. Not hold on. Why did I block that thing out? Okay. So we have the differential equation that we have to solve. Also, by the way, is my audio alright? Is my audio level alright? Actually, I can literally check it myself. I have my own stream muted. So it doesn't like go back. I have like my sounds fine, alright. No fan noise, no weird fan noises or anything, right? Or like if there's a little bit of fan noise, it shouldn't be too much. Alright, so let's solve this differential equation. Oh yeah, it's the fan noise, there is. Is it too much? But like bearable. Bearable. Let me try and apply a little bit of filter. Give me a sec. Because I think I can do a filter type. There it is. Noise suppression. I think I'm trying to use noise suppression. Let's see. Suppression level very high. How does that sound? I should check it out myself as well. Not that. I set my noise suppression. No more fan noise. Alright. Is there any more of my noise still? Oh, it's back. What? I didn't change it. What? Why is the fan noise like loud? Okay, wait, let me edit my filter. The message is delayed. Yeah, it was gone earlier and came back. Alright, what do I do that? 9 plus 10 equals 21. That is true. Oh. Okay, yeah, the noise is way too suppressed. Okay, negative 36 should be decent. Hey there, Herobrine, hello. Herobrine with colors. Alright, that should be good. That audio level should be good with the noise suppression. I think we're good. So, here we go. Differential equation. I'm in class right now. Yeah, you should be listening to this stream as well. It would help you a lot because, you know, everyone needs to solve differential equations in their class, right? Just finished a quiz. Oh, nice. How did it go? How did it go? This is a This is a Cauchy-Euler differential equation. I had my. Okay. Let's finish the quiz. I see. Got 10 out of 10. Nice. That's sick. So that's something. It is something. It's full marks. Not bad. Not bad. These are called Cauchy-Euler equation. I'm tired as fuck. Yeah, you can relax, sit in my stream and relax, trying to solve equations with me or something. This is called a Cauchy-Euler equation, which is I wrote that the stroke is a little too thick, and I accidentally deleted everything. All right, I slept for like 2 or 3 hours. Same. I've been researching a little bit on one of my homework, which I won't show here because it's a lengthy homework. So I'm like, I want to do some pun jokes again. Oh god. Oh god. Cauchy-Euler equation. Oh god. Alright. So Cauchy-Euler equation, these types of equation comes in the form of the nth derivative of y. No, I can't laugh like a maniac in class. You can't always laugh like a maniac in class if you don't really care about anyone else. Do it, Neon. Do it. So Cauchy-Euler equation comes in this form. Basically, give me a sec. Basically, Cauchy-Euler equations are equations that come in the form of the derivative, like the nth derivative of a function y that we need to find. Yeah, like I don't know how long you live. I don't know how long I'll live for either. Probably like, I don't know how long either, but how long you'll be live? But I'll be home in like an hour and a half. I might stream for that long. There isn't much homework here. I'm guessing. I don't really know. I'm not really sure about the next subject's homework because it's a little bit. It's actually a topic that the teacher never taught us. Like, professor hasn't taught us that topic yet, but like, he forgot to change the due date, so it's technically due tomorrow, even though like we haven't been taught about it yet. So I'm still doing it today, and it's not too bad though. It's like yeah, you add this on and on and on until you get to the last few terms, that is ax and then the first derivative of y with respect to x. Live as in live stream. Do you two go to the same college? Oh, that would be, I wish. Bro, that would be so sick. It'd be really cool if we did. Right? Yeah. Alright, so Cauchy-Euler equation comes in this form. How you do it is you solve it. It would be awesome, absolutely, because like it would be so cool. Like, okay, I'm gonna use x to the power of r here. It would be so cool if like internet friends all live together and like all like go to the same college together. Really, it would be super dope. Alright, so when it comes to the Cauchy-Euler equation like this, what you do is you assume that y equals to x to the power of r. Why is that? Because when you look at this, right, x to the power of r, if you take the derivative once, what do you get? You get x to the power of r minus 1. You get 1 degree less. So from x to the power of r, you get this term will become x to the power of r minus 1. And then that thing gets patched by the x over here. Give me a sec. I should change this from 0 to g of x. Alright, so here it would be so over here d to the this is the n minus 2, the n minus second derivative of y, which means that this would be something with x to the power of r minus n minus 2. If you multiply it by x to the n minus 2 over here, what you're gonna get is there's gonna be some other term in front of it, but what you're gonna get is you're gonna get something which is a constant term multiplied by x to the power of r, and it's gonna apply for this term as well. You're gonna get something with x to the power of r. Y here is already x to the power of r. This thing is already this thing will become x to the power of r as well. This term will also turn to x to the power of r, which means all of this, this Cauchy-Euler equation is going to yield us, the right hand side is going to be something with x to the power of r. Or if it's not, they're going to cancel out and you're going to get 0. In that case, it's called a homogeneous differential equation. If this guy is 0, it's going to be called homogeneous differential equation. So simply, if we look back at our equation here, we just assume y equals x to the power of r, and let's see what we can do. X to the power of 3. While I copy the equation, let's talk about something. I don't know. So like, how has the past few days been? I haven't streamed in, I think I haven't streamed in like 10 days. Has it been 10 days? Silksong, when did Silksong release? Silksong released on the 4th, right? Silksong released on the 4th, which means my last stream was on the 3rd, which means I haven't streamed in almost 2 weeks. Damn. I have a little bit to catch up on, huh? But I didn't have much homework during that 2 weeks either. I cleared pretty much all of them except for these few. Yeah, on that stream. As you can see, college, university is really chill. You have barely any homework compared to high school, at least. You see, third derivative, and there's gonna be x to the power of r, because again we assume y equals x to the power of r. Honestly, it would be great if we went to the same university, but we would be 2 different majors. Oh yeah, that's true. Yeah, because like 2 different majors would obviously be sitting in different buildings and shit. No stream because of Silksong. Yeah. But like if even then we'd still be able to like go to the same restaurant or something in the campus, which honestly is good enough. I do have a friend who's like in a different major. It's like sub major. So like I'm majoring in science. Oh yeah. I'm majoring in science. So like there's the biology, there's the chemistry, there's the physics. Obviously I go with physics. And I got a restaurant. What's it called? Just like, how do you call a food shop? That's not like a full-blown restaurant. How do you call a food shop? But yeah, I have a few friends who's in a different sub major, which we still like eat together in the cafeteria. Yeah, cafeteria. Yes, thank you. Yeah, we still eat together in the cafeteria. So like the same would probably apply. Now how do we do this? I have to take the derivative. Of course I do. Right. The first derivative is going to give us r, the second derivative is going to give us r minus 1, and the third derivative is going to give us r minus 2, and then it's going to end up with r to the power of x to the r minus 3. You add that, and then you're going to have 7x squared, and then you take the derivative twice, so you're going to get r once, and then you're going to get r minus 1, and then this one is going to be x to the power of r minus 2. So this term over here, I should actually highlight it, just so. This term over here becomes this entire thing. You know how derivatives work. But I like colors because colors are pretty. So I'm just going to highlight them anyway, even though you guys already know how it works. Or even if you don't, I highlight them because colors are pretty. I honestly should put more colors into like my my stream, because apparently, you remember last stream, for some reason it did better than my video. Like my long form video, which I edited for 3 months, it got like I had to re-upload it, so in total it got like around 300 views. And then the stream I did got like also around 300 views, which is insane because compared to a video that I made for 3 months, a stream that I set up for 15 minutes managed to get more views. I don't know how to feel about that, but part of it is probably because I put Silk Song in the title in a very well timed, because it was very well timed because, you know, the Silk Song was a huge trend at the time, meaning that I should hop on the trends a little more with the keywords. Also, I also put in a little bit more. The thumbnail was a little more interesting as well. So I feel like that that was all part of why my previous live stream went pretty well. So this x cubed here and x to the r minus 3 here combined into just x to the power of r. This one, x squared and x to the r minus 2 here, also combined to x to the power of r. So in fact, I don't have to write x to the power of r over here. I was editing non-stop yesterday. I'm so dead. Damn, how long is your video gonna be? All right, x. So that means all of these can be, you can all factor out x to the power of r, because every single term will have x to the power of r in it. Over here, x over here will become x over here multiplied by x to the r minus 1. You get the idea. This will become this will become r cubed minus this will be 3r squared, I think. Yeah, and then plus 3r. Is that right? This one will become r squared minus 3r plus 3. Yeah, and then you multiply by r. Yeah. And this one becomes 7, and then r squared minus 7. This one is minus 2r. And this one becomes just minus 10. And it's going to be equal to x to the power of 3, which we won't care just yet. We're going to just call this guy 0. We're going to call this guy 0 first, because when you solve differential equations, what you do is you first solve it in the homogeneous case. And then check Discord. All right. Oh my god. 14, that's 2 minutes, 5 minutes, 8 minutes, 11 minutes, 14 minutes, 16 minutes. And that's gonna be approximately 60. Like, that's a lot of minutes. And holy hell, that is a lot of clips. 154 clips. 178 clips on the subtitles, Neon, are you insane? 178 clips. 18 minutes. That's kind of crazy. Like, are you... You know what? Yeah, I guess that makes sense. You have to like put the subtitles for every... you have to put in the subtitles for like pretty much almost every sentence or every few sentences, right? So that, I guess that makes sense that you have a lot of... I hate audio editing so much, dude. Yeah, that's fair. Have you ever seen me edit audio in my videos before? Like, not all of them, yeah, just a few. Just a few! Just a few. It's literally... whatever. It's... Did I miss something? I did miss something. This is 7x. Yeah, this should be R. Hey look, physics homework. Yeah, it's physics homework. Indeed it is. 3... that's gonna be -6. Move inside math problem. Yeah, it's math for physics. Physics without math is like nothing. Alright, yeah. But yeah, audio editing is pain, which is why I barely do them. If you check my channel, I barely put in sound effects, like ever. Part of it is because I don't really know what to do for the sound effects. Alright, so now we have to solve, now over here we're going to have to solve for this polynomial. And then, once we do that, we're going to be able to find the x to the power of r, and that's going to be our form for this, and that is going to be our general form. That is, if we don't have g here, if we don't have gx here, what is going to be the answer to y? From that, we get the general form. You can use the general form to calculate, to find the value of the specific form. That is the form where, that is in case there's x to the power of 3 over here, which means that's gx over here. If that exists, then you're going to have to, the solution that would give you this gx over here is called the particular solution. And you can find the particular solution by solving for the homogeneous solution first. The homogeneous solution means you set g equals 0. You set g equals 0, you get the solution. You use that solution to find the case where g isn't 0. So in this case, right now we're trying to find the case where, you know, g isn't 0. So let's do that. How do I solve this polynomial? Let me try plug in 1. If I put 1 in there, it's going to be not 0. If I plug in 2, that's going to be 8 plus 4 times 4 is going to be 8 plus 16 equals 24. Minus 12 minus 10 is not equal to 0. So that doesn't work either. So if we set r equals to 5, what happens? R equals 5, this becomes 1, 2, 5, this becomes 1, this becomes 1, 2, 5, this becomes 100. Add them up, that's even worse. So what if r is -1? What if r is -1? If r is -1, this becomes -1, this becomes +4, so -1 plus 4 becomes 3. This becomes +6, so 3 plus 6 equals to 3 plus 6 equals to 9, subtracted by 10, you still have 0 over there. Okay, so what if r equals to, well, this is fun. So what I'm doing right now is I'm checking 10 over here. 10, you can, the factors include 1, 2, and 5, right? And also 10, yeah, I almost forgot about 10, but it definitely isn't the answer here. 1, 2, 5, and 10. So r is probably one of these guys. That is assuming that it's correct. R is probably 1, 2, 5, 10, or some plus or minus of those guys. I'm guessing. Darkness Man is mathing. Indeed, I am. This is in the case where you can factor the polynomial, but right now I'm actually I'm starting to doubt if if I'm doing this right. I may have factored it incorrectly. This one, I in fact did factor it incorrectly, because over here this term is not 3. Why did none of you guys warn me of this? I'm blaming on you guys. This one is not 3, this one is supposed to be 2, and then you multiply by r, and then this term becomes 2, which means before this was plus 3, it now becomes plus 2, which means now it becomes negative 7 over there. Which means it becomes negative 7 over here. I don't think I got anything else wrong. This becomes, what the hell? This is 7r squared minus r, so that's going to be 7r squared minus 7r. This is minus 2r, and this is minus 10, okay. So let's try that again. If I plug in r equals 1 here, it's going to be 1 plus 4 becomes 5. Nope, not that doesn't work. If I set, if r equals 5, right? If r equals to 5, what we have is we're going to have 125. Nope. If r is negative 5, we're going to have negative 125 plus 100 minus, no, this will be plus 35 minus 10, which indeed is equal to 0. Therefore, one of the possible r's is negative 5. So this means we can, this means that we can turn this into r minus, no, we can turn this into r plus 5, and then some other polynomial with r. Now I don't really know what that thing is going to be, so let's try to find it. The first term is going to be r squared, obviously, and now I just have to do some polynomial division. So r to the power 3 plus 4. Have you guys forgotten how to do polynomial division yet? One of my friends actually has. Okay, so this becomes r plus 5. You guys remember how to do this? If I multiply this by r squared, we're gonna get r cubed plus 5r squared. Ah, yes. And then you subtract that, that becomes negative r squared. The technique. Yeah. Really annoying. I honestly never liked polynomials because it's just big numbers. It's just so many terms you have to deal with. I never really liked them. But like, yeah, it's overall just annoying. And this is negative 7 minus 5, so if you subtract them, you're gonna get negative 2r. This negative, so this will be negative 2, which gives us r squared minus 2r minus 2, not 2r. Why did I say 2r? I'm stupid. And then in turn, this is equal to, there's definitely negative 2 in there. Yeah, so this will become r plus 5 times r plus 1 times r minus 2 equals 0. And that is our polynomial, which means that the possible value of r is, the possible values of r are negative 5, negative 1, and positive 2. Therefore, this is the value of r that we found, which we found from from assuming that y equals x to the power of r. Therefore, if we plug this back in, we're gonna get something that will 0 for okay. Yeah, we found r from assuming that y equals to x to the power of r. And then it turns out that, yeah, y equals x to the power of r. And those r are these guys. Therefore, the general form the general solution is we're gonna have three terms. We're gonna have the first term, which is x to the power of -5. The second term is gonna be x to the power of -1. And the third term is gonna be x to the power of +2. This is the general solution to this problem. All right. That means for any, we can choose any C1, C2, and C3. It can be like 1, it can be like 1, 2, 3, or it can be like 5, 6, 7, or it could be anything. And if you plug this YG back into this, we plug the YG, if we plug that Y back in here, the right hand side is going to turn to 0. The right hand side is going to turn to 0, which is the homogeneous solution. So that's our YG. The next thing we have to do is we're going to have to find the particular solution. We have to find YP, the particular solution to this equation, which means that before this, right? This whole thing, you plug it in, you're gonna get 0 on the right hand side. But now if we successfully find YP, if we plug in YP, the right hand side is gonna turn into x cubed instead of 0. And that's why it's called particular solution. It's for this particular function on the right hand side. It's for general solution, it means that it works for anything for 0 on the right hand side, and for particular solution is for this particular function. All right, so finding YP, there are several ways you can do this. In fact, there are like 5 ways. If I remember correctly, there are like 5 ways, or 4. I actually don't remember. But there are like several ways that you can solve it. So give me a sec. Let me go check the ways real quick. There's like the way to use the annihilator method. There's the undetermined coefficient method, and there's the reduction of order method. Which personally, the reduction of order method, it seems to be like the best, the most, how do I put it? It's the most effective way, I think. So basically, what we have to do is we have to find YP here by finding the Wronskian of these guys. So first of all, I'm going to denote them. I'm going to denote this as Y1, Y2, and Y3. I'm going to denote it like this. I have a confession. What is it? After I enter biology, I miss math. That's fair. And yeah, I'm fairly proficient in terms of mathematics, and that's why I came to physics. I didn't go to math because it's way too, I don't know, rigorous, I think. I'm not really the most rigorous person in terms of mathematics, but yeah. So from here, we can find the YP using the method called the reduction of order, which the teacher did not provide a proof for. So I'm just gonna straight up bring up the formula for it. The formula for it is, if I remember correctly, which I could be incorrect here, is that YP is equal to this following abomination. It's equal to the summation of J. Yj. Okay, still seems pretty normal. And then we have this big ass integral, which I didn't draw very well. So let me try and like draw it. Too fat. Come on, I can do better. Fuck it, I'll keep that. All right, and this is how you can find it, if I remember correctly. Times gx and divided by the overall Wronskian. All right. So this is our solution. Now the question is, what the fuck does this mean? What does all of this mean? Well, the answer is that all of this is basically just, how do I explain this? Let's explain one by one what each symbol means. First of all, the first symbol that I want to point out is the W here, called the Wronskian. Basically, the Wronskian is the determinant of this function, of this, well, matrix. y1, y2, y3, y1 primed, y2 primed, y3 primed. Okay, wait, hold on. Wronskian is equal to that. Divided by y1 double primed, y2 double primed, and y3 double primed. This is the Wronskian of the in our case at least. If we have four particular solutions, that is, if we had like the fourth derivative of y, we're gonna end up with four y terms here. Okay, if we had four derivatives of y's, we're gonna have four different values of r over here. And if we have four different values of r over here, we're gonna have four different terms of y1, y2, y3. We're gonna have y4. And if that's the case, we're gonna have to add in another column. We're gonna have to add in y4, and we're gonna have to add in the y triple prime over here as well. So like, if we had four order, it's gonna be a huge pain in the ass. Fortunately, we only have three, so we can kind of find the determinant of a 3x3 matrix much more easily. My viewership is dropping, which implies that I'm starting to sound incomprehensible. I'll try my best. Let me drink some water. I'll try my best to make it comprehensible. Alright. So in our case, let's find W, the Wronskian here. The Wronskian for our case, y1 is x to the y1 is x to the negative 5, y2 is x to the negative 1, and y3 is x to the power of 2. So the Wronskian is going to be the determinant of this matrix. The Wronskian is equal to x to the negative 5, negative 5, x to the negative 6, and positive 30 times x to the negative 7. This is y1, and then you take the first derivative, you take the second derivative. The next term, y2, is x to the negative 1, so we just have x to the negative 1, and we have negative x to the negative 2, and we have 2x to the negative 3. Lastly, it's going to be x squared, so it's going to be fairly simple. We have x squared, we have 2x, and then we have just 2. And we have to find the determinant of this matrix. How do you find the determinant of the matrix? What you do is you multiply them diagonally. So when you have a 3x3 matrix like this does not generalize to 4x4, but this is why they gave us 3x3, because it's merciful. What you do is you multiply the diagonals like this. And if it hits the wall like this, you loop back over to this guy. So like down, down, and then you loop back over to here. And this one, you go down and you have to loop back over to this guy. And that is how you find the first part of the determinant. The next part of the determinant is found by multiplying almost the same thing. But so the first part, I'm gonna write the first part right away, I guess. So as to make it make sense. So we're gonna have negative 2x to the negative 7. This is the first diagonal line. And then this is it's gonna be 2, this is gonna be plus 30 x to the negative 7, because x to the negative 1 here, cancel that thing out, it actually becomes plus 60, sorry. That is from the second diagonal that we went through. We went down here and loop back over to this one. Then we have this one again. We go from here down the diagonal, we loop back over. So we have x to the power of 2, and then there's going to be x to the power of negative 9. So it's going to be x to the power of negative 7 again. X to the power of negative 7, and then this is x to the power of 2, is negative 5, is positive 2, so this is actually going to become negative 10. And this is the down diagonal. Next up is you have to add in the, no, you have to subtract it by the up diagonal. So you're going to have to subtract it by this diagonal multiplied. You have to subtract it by this diagonal, again loop back over. Then you have to subtract by this diagonal. So let's do that, and we're gonna subtract it. How do we do that? Wait, if we subtract that, what do we do? Subtracted by the downwards diagonal, we're gonna have negative 30 x to the power of negative 7. Two, 2, 1, so that will become 4 x to negative 7. I know that it's probably going to be x to negative 7, like for all of them. 2, negative 5, yeah, so it will be negative 10. And then it's x to the power of negative 7 again. So the Wronskian here is going to be equal to what? It's going to be equal to negative 2 plus 60 minus 10 plus 30 minus 4 plus 10 times x to the negative 7. And if we do the calculations, there's going to be 90, there's going to be 100, there's going to be negative 12, there's going to be negative 16. So it's going to be 100 minus 16, which is going to be equal to 84 x to the power of negative 7. Someone check that. And that is what we have down here. Yay. Obviously we're not done here. What, do you think would be done? No, obviously not. This is differential equations we're talking about. Differential equations, you have to solve for so much. So, now we know that the Wronskian of this system is equal to 84 x to the negative 7. Okay, moving on. Let's see what W with subscript J here means. Oh, we're running out of space? No, we aren't. No, we aren't. Wait. Is there any part that I can move? Yeah, I think I've been using the space a little bit too much over here, so I'm gonna shrink it down. No, we're not using up too much space. I'm just gonna move all these up. I'm also gonna shrink it down. Move this up here. Alright, this is gonna take a long time. Yeah. Welcome to solving differential equations, my friend. Welcome to solving differential equations. It's kind of a pain. Alright. And then I think I can delete layer 3. I can delete layer 3, yeah. Okay. So this is the Wronskian. Gonna box that in so we know later on that it's gonna be important. Next up is, what is WJ here? Well, WJ here, the math hell is waiting for us. Yeah. The gates of hell is open. Let's say if we have 1, what does this mean? This means we replace the first column by 0, 0, 1, and the rest just stays the same. this is y3 prime, y3 double prime. This is what the Wronskian with 1 down here means. Obviously, if this, so over here, wj here means that if j's, we're summing over j here. We iterate from j equals to 1 to j equals to 2 to j equals to 3, and then we add up all of those answers. So for the case where wj equals to 1, it's going to be the determinant of this matrix. In the case where it's equal to 2, then the middle column is going to turn into 0, 0, 1 instead of the first. The first column is just going to become y1, y2, y1, y1 prime, y1 double prime again. And the rightmost column is, for w3, the rightmost column is going to be 0, 0, 1. So in our case, let me find w1. w1 is equal to, well, we can easily calculate that because we already have this one, and then we know that w1 means this term goes to 0, this term becomes 0, this term becomes 1 instead, which means that 0, this diagonal doesn't matter, this diagonal doesn't matter. The only diagonal that matters is this, is the one that comes from x to the negative 1 to, it's the only one that comes from here. In this case, it's going to be equal to 2. And then, of course, the up diagonal is, the only one that matters is the one with this guy in it. So up like that is going to be 1. Again, the w1 here means we replace this with 0, 0, 1. So the up diagonal is going to be 1 times negative x, yeah. So this is going to be negative 1. So the w1 here is going to be equal to 3. Let's find w2. w2 here means that the middle column becomes 0, 0, 1 instead. Which means the diagonal the only down diagonal that matters is x to negative 5, x to the negative 6, and then 1 over here. So it would actually become x squared times that is going to be negative 5x to the negative 4. And you subtract that by the diagonal, the up diagonal. So 2x to the negative 3, this actually turns into 1. So this goes to 2, and then this goes to x to the negative 5. So this becomes 2x to the negative 4, which is going to be equal to negative 7x to the negative 8. And then we have w3, which is equal to, again, it's just the same thing. It's negative x to the negative 7 and subtracted by the upwards diagonal, which is going to be equal to negative 5, yeah, negative 5x to the negative 7, which means all of them will become 4x to the negative 7. And that is our Wronskian w1, w2 to w3. Which means we can finally find yp, because yp is equal to, give me a sec, I need to delete that, delete these random lines, which means that yp is equal to y1 times the integral of w1 times g divided by the w, and this is dx. And you add that, and next up you add y2 w2 g divided by w dx, and add y3 integral of w3 g divided by w dx. All right. Let me stretch real quick. Okay. So let's do the calculations. So wx is 1 over 84. wx is 84, so this part will become 1 over 84 later on anyway. So this becomes 1 over 84. And this is y1. y1 is just x to the negative 5. And we have to integrate what? 1 over w here becomes x to the 7, x to the power 7. G here is x to the power 3, and w1 is equal to 3. So that gives us this term. The next term, y2, is equal to y to the negative 1. No, x to the negative 1. X to the negative 1, we integrate it by w2 and g. w2 is negative 7 times x to... Okay, so this will become negative 7, x to the negative 8, g is x to the power 3, and w here is x to the power 7, because, well, w we pulled out the divided by 84. And it becomes dx. And then lastly, we add in y3. y3 is x to the power of 2. And you integrate it and you have 4x to the negative 7 times x to the power of 3 times x to the power of 7 dx. And all of this is, are all in a parenthesis for the sake of convenience, and it doesn't lose any generality. I'm going to set the integration factor to all be 0. So this one becomes 1 over 8 to 1 divided by 84. This is x to the power of 10 integrated will become x to the power of 11 divided by 11. And then x to the power of 11 divided by 11. Okay, so it's going to be 3 over 11 times x to the power of 6. This term is x squared. Wait. Something's off. They do it right. I must have done it right. No, wait. I did it correctly, yes. But the dimension is inconsistent. Is it? There's x to the negative 5. This is 3x cubed. This is going to become x to the negative. This is going to become x to the 10. So it becomes x to the 6. This one is x squared, which becomes x to... Wait, what? I may have done something wrong. Give me a sec. W2. The Wronskian 2 here means we set this to 0. We set this to 0. We set this to 1. Which means it becomes x to the negative 4. Ah! Your 7th stream? Goddamn, yeah. I haven't streamed in like a few weeks actually. Also, I found out where I got wrong because for some reason adding up x to the negative 4 turns into x to the power 8 for some reason. That reason is because I'm an idiot. And I put it on the wrong layer. This was supposed to be x to the negative 4. And I forgot to change the colors. Okay, this should have been x to the negative 4. I'm just stupid, don't mind me. So this becomes x to the negative 4. So this whole thing becomes x to the power of 6, which becomes x to the power of 7 divided by 7, which means this will become just negative x to the 6. Because negative 7 cancelled out. Negative 7 cancel out with the divided by 7. Over here, it's the same thing, just x to the power of 3 will become x to the power of 4 divided by 4, cancel out with that 4, so it becomes x to the power of 6. So you add in x to the power of 6 again. What's this supposed to be? This is the, I'm solving the differential equation. I'm solving this differential equation using the reduction of order method. Yeah, I'm using the reduction of order method by using the formula that uses the Wronskian of the functions. The formula was handed down to us by some divine being, that being our professor. And I can probably prove it, but I probably won't. I think it's not. I don't want to. I just don't. Why can't I write? Right, that's why. Okay, there we go. So this will negative x to the 6, and I thought you finished them weeks ago. How many DE did you have? Well, this is just I have a course on differential equations, so I have like a bunch of. So I just have new ones every week. This is one of them, obviously. This becomes x to the power of 6 divided by 28 times 11, which is equal to 318, I think. And this is our particular solution. And I'm going to move all of this. I'm going to shrink all of these down so that we would have some more space to work with. All right. And therefore, the overall y is going to be equal to c1 x to the negative 5 plus c2 x to the negative 1 plus c3 x squared. I just had DE in my Math 3 course. I don't know. I feel like DEs are like, you can't really cover them with other stuff. Because like differential equations, you have to, apart from the basic ones, you still have to like learn shit about like what partial differential equations, because it is part of my course. Partial differential equations are part of my course. There's also the Laplace transform. There's also a few of the special functions that would help with differential equations. And there's also the Fourier transform, which is also very cool, and it's also helpful in solving differential equations. So yeah, overall, a pretty interesting subject, if not tedious. Also, y is going to be you're going to have to add in x to the power of 6 divided by 318 as well. Okay. And that is our answer for y. Not yet, because we have to plug in the initial conditions. All right, let's just do it. So how many questions are in this assignment? 1. Literally just this one. They tend to be pretty long, so I guess that's a mercy. That's a merciful thing. And then after this, I'm going to be dealing with calculus 3 problem. So when y at x equals to 1 should be equal to 0. So c1 plus c2 plus c3 equals, have you taken flux yet? What do you mean by flux? Because there's actually a lot of things regarding fluxes. Like in which context? Because there are a lot of things regarding fluxes, but I'm not the most familiar with all of them. Okay, if I take the first derivative, this is going to be negative 5 c1. I kind of want to zoom in there a little bit. I've already forgotten what I took last year. That's fair. So did I. The fuck did I take last year? Right, I took biology, which is the reason why I didn't remember them. Yes, I'm gonna continue to piss on biology because I dislike that subject. It almost costed my A. It didn't though, but you know. This becomes x to the power of 6, so this becomes 6 divided by 318. So 318 divided by 6 is equal to 5, and then you have 1 there, and you're gonna have 53. Wait, what? 84 cancels out with 3. That becomes 28. You multiply it by 318. It's not 31. You multiply by 11, and it's not 318. It's 308. I'm stupid. It's 308. This is 308. I'm absolutely tired right now, but I'm here. Hello, welcome. Welcome to the stream. Item review. This was supposed to be 308. So that's gonna be 3 over 154. Yeah, and it should be equal to what? It should be equal to -7. Hello, welcome to the stream. Welcome to the stream. Seems like you just got doxed there. Doesn't really matter though. None of you guys can pronounce that. Y double prime 1. Also, how's Silksong doing for you? It's a fucking great game. The game is so big though. Like, I'm 30 hours in. I'm 30 hours in, and I think I'm only like 70% done with the game. At least for the main ending, for the non-completionist ending. Like, if it's for the completionist ending, then I'm probably only like, I'm probably like only halfway through. Well, yeah, hello. How do you write your brother's nickname? I have no clue. The top hat, hello, that top hat. Yeah, welcome to the stream. This, we're solving differential equations. Alright, if I take the second derivative, what we're gonna get is we're gonna get first derivative is gonna be -5, second derivative is gonna be positive 20, so it's gonna be 20c1. This one first derivative is gonna be -1, and then second derivative is gonna be positive 2, so it's gonna be plus 2c2. Looks like someone had a great time after their homework. Oh, absolutely. The game is very difficult. Silksong was really difficult, but I had a lot of fun. First derivative, yeah, and then this one is second derivative is gonna be 30, so it's gonna be 30 divided by 308, and it's gonna be equal to 44. Did I make a mistake? Why is the number so bad? Why is the number so messy? I don't want to deal with any of these numbers. Holy shit. I'll consider this done. We're gonna end up with C1. Okay, wait. Gonna zoom in. We're gonna end up with C1 plus C2 plus C3 equals to -1 over 308. And then -5c1 minus c2 plus 2c3 equals to -7 minus 3 over 154. And then lastly, it's going to be a 20c1 plus c2 plus 2c2 plus 2c3 equals to 44 minus 15 over 308. Alright, And now we have to solve this damn problem. Can I just give up? Can I give up? I kind of want to just give up here and then just let the rest just... fine, I'll do it. Okay, so this one is equation 1. This one's equation 3. What I can do is I can subtract equation 3 by equation 1. Equation 3 subtracted by 2 times equation 1. And we're gonna get 18C1 is gonna be equal to 44 minus 15 over, no, this is 30 over 308 minus 30 over 308 plus, okay, I'm back. Welcome back. Welcome to the stream. We're now solving this abomination to find the answer. So this is minus 30 over 308. OMG the math. Yeah, I know, right? I kind of want to just give up on this one, honestly. But like, we are already here, so might as well just divide that, and we're gonna get 44 minus 30 plus negative 30 plus 2 is equal to negative 28 divided by 308, which is equal to 44 minus 1 over 11. 44 minus 1 over 11 is equal to 484 minus 1 divided by 11, which is equal to 483 divided by 11. 483 divided by 11 is divisible by 3. On the left hand side is 18. So C1 equals to 483 divided by 11 multiplied by 1 over 18. And it's equal to, this is 6, this is going to be, for is 16, 161. Okay, so it's going to be equal to 161 divided by 66. Who came up with this? 161, 161, is 161... What's 161? 161 is divisible by, it's not divisible by 3. It's divisible by 7. It is divisible by 7, but down here it's not. It's divisible by 7, but that's kind of just it. So, well, we got C1 though, at least. The rest should be relatively simple. Sometimes the math professors want to do a little trolling. I suppose so. Alright, so this is C1. So now we can find C2 plus C3. It's equal to negative 1 over 308 subtracted by 161 over 66. Oh my god. And then negative C2 plus 2C3 is equal to negative 5, so that becomes positive 5. That's 7 minus 3. That's going to be negative 7 minus 3 over 154. Are you guys having fun, chat? Are you guys having fun? I'm not. And you add it by 5, and which multiplies that guy up there, which is going to be 5 times that, which is going to be equal to 805 divided by 66. Oh my god, what? What is this? I'm tired. That's how much fun I'm having. Fair. I mean, someone said that they enjoy your suffering. Fair enough. That is, honestly, yeah, fair. I don't really... I suppose viewers do like to see their streamers, like, suffer or something. Honestly, that's valid. This becomes 3c3 equals to negative 7. If you add them up, this becomes negative 7 over 308. 7 over 308, it is divisible, but what do you get? 7 over 308 becomes 444. This becomes 1 minus 44. And this one becomes 805 over 66, which fortunately means that they have a common denominator of 11, like the common factor of 11, which means if I multiply this thing here by 3 and multiply this thing here by 2, we should be able to combine them. It's funny to have friends that struggle when you clearly know how to help them. That is true. It is. I can't deny that. Okay, it's gonna be 3 over 44 is 4 times 11. You multiply that by 3 and you're gonna get 12 times 11, which is gonna be 132. This one you multiply by 2, so you're gonna have 805. This one you're gonna end up with 1610. Okay, just calm down. It'll be all right. This will be 1617 divided by 13. No, this 1607 divided by 132. And is there any thing that we can do with this one? I think it's alright, just a little hard. Okay, if I divide this by 11, can I do that? That's gonna be 5, and then we're gonna have 44, so we have 6, 7. Nope, you can't. We're doomed. This is it, guys. We're done. So C3 is going to be equal to negative 7 over 3 plus, you can't even divide this by 3. It's plus 1607 divided by 396. So that's a C3. I want to... Jesus Christ. Please stop. Okay, now we have C3, so now we can find C2, which is the last piece of the puzzle. So C2 equals to negative 1 over 308. 1 over 308 subtracted by 161 over 66. 66, you multiply by what to get 308? You can't. Okay, never mind. And you subtract, and then you add 7 over 3, and you subtract 1607 divided by 396. And that's our value of C2. I don't care anymore. I'm not going to simplify this. It's up for the rest is just, yeah. Y is going to be equal to C1 x to the negative 5 plus C2 x to the negative 1 plus C3 x squared plus what? Hold on. Plus 1 over 308 x to the power of 6. And this is our answer. I'm done here. Well, yeah, it's hard, just agonizingly long. Yeah, it is a pain. I don't want to do this in the exam, man. I would give up if I see this kind of question in the exam. Anyway, I'm gonna save that so that I don't have to do it again, like later on. Let me save this somewhere. Boop. All right, and it's been saved. Oh, hello. Oh, you mean that one game series? All right. So that, oh, whoops. Okay. So, new page because we have another homework that we have to do. All right. So that's our differential equation homework completed. Yippee! Why is it so painful? All right. So next up is a little more fun, I think. Personally, I find it more fun because it's more, at least I think it's more interesting. This is actually part 2. I've done this bit before. I've done the first question of this homework set before, but I haven't done the rest. So I'm gonna go ahead and do that. Paste that there, and we have this first problem. Show that the curvature capital T of a curve described by the vector value function r t is given by this function. Okay, so here's a cool little detail about this homework. My professor hadn't taught this. My professor hadn't taught us about this yet. I think he's like he's unable to like he's kind of busy, so he couldn't get this in the lecture yet. But he forgot to set the due date, which means that this homework, which we hadn't been taught how to do before, is due tomorrow. Actually, no, it's not due tomorrow. It's due today. It is due today. Yeah, it's around a few hours. Now, what the fuck is a curvature? He's busy playing Silk Song. Oh, I don't know what a curvature is just yet. Fortunately, the next question gives us a clue as to what the curvature is. So before I do the second question, I'm gonna go ahead and do the first question first. No, the third question first. So I'm gonna create a new page that we can do the third question on. So, if a particle moves along a smooth curve C, then the velocity and the acceleration at each point of the curve is given by these following values. Streamer doesn't know. Okay, so if a particle moves along a smooth curve C, then the velocity and the acceleration at each point of the curve is given by that function, given by these. So what does this mean? Give me a sec. Wait. All right. So what does this mean? It means that, well, as its name implies, a particle moves along a smooth parameterized curve, right? So what this means is we have a function. We have C here. It's a function of something. We have C here is a function of, maybe we can call it time, parameter time. This means that it's going to be equal to Cx as a function of time along the x-axis, plus Cy as a function of time along the y-axis, plus Cz as a function of time along the z-axis. That is, the curve, what a curve is, it's basically, what a differentiable curve is basically, a curve is a function that maps a real number onto a vector. Okay, so let's analyze what this means real quick. This symbol here is, this arcane symbol basically tells us that C is a function. C is the curve function that takes in an input that is a real number, one real number. It takes in the input as one real number, and then it's going to change, and then that input is going to get mapped onto a vector that has n elements. So in our case, there's this is a 3 vector. This is a 3-dimensional vector, so n here is 3. In general, though, the curve is basically a function from a real number to any to a vector. Yeah. So if a particle moves along a smooth curve C, then the velocity and acceleration at each point of the curve is given by that. And we're gonna have to prove that, and by proving that, we're gonna find out what kappa is, which is gonna help us solve this problem before. All right, does this make sense? This is basically the domain of the function. This is basically the range, aka image, aka codomain. This is the function name, this is the domain, which is basically the set of the inputs, and then you map it onto the set of the outputs. So if a particle moves along a smooth curve C, then the velocity and the acceleration at each point of the curve is given by the following. So obviously C here is a vector function, it outputs a vector. So if we have a C over here, really this vector tells us where something is at a function of time. What this vector does, it tells us, this curve tells us where something is as a function of time. So let's say if we have a 3D axis. Let me do a little bit of right hand rule real quick. So x goes this way. Is y normally like green, or is y normally blue? Whatever. The curve, the smooth curve, basically tells us where something is as a function of time. Like this, let's say at time t equals 0. Hold on, let me pick a color. Let's say at time t equals 0, the point is over here. And after time goes on, the particle just moves along this path. This path is what represents the curve over here. So yeah, that's what the smooth curve here means. The smooth curve, the fact that the curve is smooth means that it is differentiable. So really what this means is basically this curve just explains us the position of something, a position of a particle as a function of time. Which means the velocity vector as a function of time, of course, is going to be equal to the rate of change of the position vector, which is the curve function itself. So, well, that's literally by definition what the velocity is. The velocity vector is the change in position over a small amount of time. So this is what the velocity is. We can just now we have to prove the fact that this velocity here is equal to this thing, this what is it called, this expression over here. Well, what is this expression? This expression basically is comprised of two parts, and I'm gonna write it in a way such that it will take on this form. So the velocity vector here, you can use chain rule to change it. ds here is the reparameterization of the curve. Basically, instead of tracking the position of something with time, you track it using the arc length. So like if we set s equals 0 over here, as you move along the curve, s increases depending on the length of the curve that you traverse. So like over here, s equals something is equal to the length of this curve. On the other hand, it might not be the same for time. So maybe the particle just comes over here and then just stand here for a little bit and then just continues to move. In that case, well, time isn't doesn't really tell you the length of the curve anymore, does it? So that's what it means for, so that's what S here means. S here is the arc length of the curve. And we are basically reparameterizing it. This becomes dr by ds, which is the change in position over how far you moved. Obviously, the change in position over how far you moved is going to be a unit vector, because this is the length, because this is the direction. Okay, r here is the direction that you moved and the distance that you moved. ds here is the distance that you moved. So if you cancel them out, all you have left is just the direction that you moved, which means that this is going to be equal to ds by dt times the unit vector for velocity, which itself has a name known as the tangent vector. It's called tangent vector because it's pointing in the direction where you move next. Yeah, it's tangent to the curve. So if I were to draw it here, it would look something like this. If I could afford more pixels. All right, so that's what this means. ds by dt and t. Yeah. So that's the velocity vector. What else is there to talk about? I think I explained it well enough. It's just saying, okay, ds by dt here is just how far you move. You know, the arc length, the length of the arc that you move, divided by the time it takes to move along that arc. So obviously over here will become the size. So over here, ds by dt becomes the velocity. No, this ds by dt here becomes the speed of the particle. Then t hat over here shows us in which direction it's moving. So you multiply these two together, you get the velocity vector, which is the speed and the direction of the particle. Makes sense? It should make sense. Although next up, it's a little bit more complicated. Next up, we have the acceleration vector. Also here, give me a sec. Also from here, we have successfully defined that t is equal to dr by ds. All right, next up is a, which is the acceleration vector. Obviously, the acceleration vector is going to be the change in velocity over time, right? By definition of what the acceleration is. That's literally what it means. All right. But we already know that the velocity vector here is equal to this thing. So we can just change this into the derivative, like we can change it into this derivative right here. And then we just, just do that. Just use the product rule. You know how the product rule works. You differentiate the first term, and then you leave the second term intact. And then you differentiate the second term while leaving the first term intact. That's not by ds, that's by dt. And then again over here, this term we can use chain rule for. So we can change this in d squared s by dt squared, the second derivative of the arc length with respect to time. Which this one just basically the tangential acceleration. This one becomes the tangential acceleration, while this term becomes ds over dt squared, and then we have dt hat by ds, which is equal to, give me a sec, to recopy all of that, second derivative with respect to time, and then that becomes ds over dt squared, and then we have dt by ds. What is dt by ds? dt by ds is the rate of change. Well, is the how much. What is it? Well, let's look at what is the differential of. Okay, so dt is the dt is a delta rho, right? Obviously. So that means if our path curves a little bit, so our t over here goes in this direction at this point. Let me put calendar for me. All right, good luck. This one is t. Yeah, this one is gonna be t at a certain value of s. Fuck, I drew on the wrong layer for the entire time. Well, forget it, we'll be fine. T here is at this s, at this value of s. And then there's the next t, which is the new value, which is the new tangent vector. You don't have to stream, you just can just no record. All right. S plus delta S plus ds. So as you can see here, as we move along the curve, this is the curve, and then over here the tangent vector is this thing, t of s. But then as you move further, the tangent vector changes. Here I exaggerated the change quite significantly, but basically as you move along this line, the length being ds, the tangent vector changes along that line. In fact, the change of the tangent vector is the normal vector. Let me just draw delta t. It's gonna be this one. Hello, the guy who randomly came to VC, questioning me if I'm doing what the VC name says. No way you forgot how to pronounce my name. I haven't, don't worry about it. So we can just draw this this vector out, and then you just subtract them by the later vector subtracted by the original vector down here. So you end up having this. So come on, trust me. Have some trust in me. So this is going to be the new delta t vector. This one just happens to be the normal vector, the vector that's normal to the curve. It's perpendicular to the curve. As ds here gets smaller, it gets closer to being normal to at a certain point. So that's what this so that's what we need to find. Obviously, if if you change ds by just a little bit. Okay, wait, hold on. And okay, hold on. Give me a sec. All right. If we define this to be the normal vector, well, not really define it to be a normal vector. This vector is going to be dt by ds. This is the change in the tangential vector. Again, its direction is going to be perpendicular to the okay, sorry, my pen fell. The direction is going to be perpendicular to the curve, to the tangential vector. This one, therefore, we're going to define this to be the curvature times the normal vector. All right, let's slowly go over what this means. If the curvature is high, that is, if it's very curved, let's say if the direction slowly changes, the tangential vector, as you move along here, changes only a slight amount, right? As you move from here the tangential vector is like that. As you move from here, the tangential vector is like that. It doesn't change that much. So the curve here, it curves a little bit. On the other hand, if you have this thing that curves like a lot, let's say for example like this, it curves a lot. So if you move from here, which has the tangential vector in this direction, and then you come over here, the tangential vector is in a completely different direction. Hello, science or math. Hello, I'm a math guy. Yes, welcome. Welcome to the stream. Yeah. Welcome you all to the stream. Thank you for viewing. All right. So the more it curves, the more the tangential vector changes, which means the higher this whole thing is. We define n here to be a unit vector. We define n to be a unit vector. Therefore, kappa here is the curvature, which is the size of the change of the tangential vector. How quickly the tangential vector changes. The more the curve, how do I put it? The more curvy the curve is, the bigger this number is. The less curved the curve is, the smaller this number is. So from that definition, we can finally say that this is equal to kappa n. And this indeed tells us that if a particle moves along a smooth curve C, then the velocity and acceleration can be given by this whole expression indeed. As you can see, we have successfully proven. I was forced to join. Yeah, nice. So as you can see, we have indeed proven that it is equal to this. This is true. We have proven that this statement is true. In fact, what we did was we defined what t is, and we defined what n and kappa is from this question. So the main takeaway for this question really is just that first of all, it's just we now have the definition. We now have the proper definition. That is, the tangential vector is equal to the change in position divided by how much you walked along it. It's just the direction that the curve is going in. And then we have I should write this to me like equivalent to or like defined as kappa n here is defined to be the change in the unit vector as we move along the curve. All right, and these two are integral for solving this problem over here. Show that the curvature kappa of a curve described by a vector value function is given by this. All right, so it's given by this. So let's take a look at what it is. Kappa here, as previously stated, kappa is the size of this vector. By definition, kappa equals to the length of dt by ds. Yeah, all right. Well, now what? Hold on, wait, is that right? Let me test out the desmos.com real quick. Let me find alpha t equal to, I might as well just share my screen for the Desmos as well. Where GX? Where's my Opera GX? It's not capturing my Opera GX. Oh, hold on. Let's say I have r cos t, r sin t, and then t. All right. Okay, wait, give me a sec. It's not able to find my over GX. Okay, why don't I just remove that window capture and just make it again? Create a new capture output, window capture, add source, add a new source instead. I'm gonna call it. Yeah, it is. Yeah, indeed, I am from Thailand. I'm gonna call this Desmos capture. All right, and then I find, there it is. All right, there we go. There we go. Now it's working. It's a little too big. Let me just hide it. Okay, there we go. I'm buried. All right, now there we go. All right, I haven't put any weird shit on my tab, have I? All right. So this alpha t. So now I'm just gonna plot out alpha t, and I'm gonna set t equal to any number from like 1 to 100, and then I'm gonna zoom out a little bit. And this is the curve that we're talking about. As you can see, this curve is no tester really the guy who said we try. All right, as you can see, this curve is curvy. This is just an example of the curve, obviously. Let's see what happens if I take the derivative of this. What we should get is we should get the velocity vector, right? What we should get is we should get the velocity vector at a certain point. I'm going to set t equals to 1. So now we can now write we can write a vector at alpha big T, and then alpha big T plus v big T. That works, right? That works. Yep, perfect. All right. So here, as you can see, as we move, it's not really that clear. Let me reverse contrast for dark mode real quick. There you go. And then I'm gonna make R a little bigger and then make it a little more coiled up. So as you can see here, the velocity vector here is indeed tangent to the point, to the curve indeed. And that is the velocity vector that we wanted. Now, what the tangent vector, what the tangent vector here is you have to take the derivative with respect to s. But here it's a little bit of a problem because we can't really differentiate it like that. Mainly because, well, Desmos doesn't really support reparameterization, which means we can just use a new definition, which is the fact that the t unit vector goes in the same direction of the velocity vector, which means I just have to take the absolute value. I shouldn't have used t as being this one. I'm going to call this t tangent vector, and it's going to be equal to the absolute it's going to be equal to v over absolute v t, which makes it much easier. So now we have a unit vector that is going to be so many tabs. Do you think there's many tabs? My main over GX browser has 549 tabs. Compared to this has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. This has 17 tabs. There's like nothing compared to my main over GX, which has, I think, 549 tabs. I think you lost your mind, kind of. I mean, I'm studying physics. What do you think? All right, so let's let's redraw that. Let's redraw the tangent vector, but let's redraw the velocity vector, but now we replace it with the tangent vector instead. That is, we change this to tangent. We change this to the tangent vector, and as you can see here, it is still the velocity vector. He's a gamer and physics guy. What do you expect? Yeah. Here, as you can see, sorry. As you can see, the tangent vector is indeed 1 unit long. I think in... Wait, is that actually 1 unit long? I don't think it's 1 unit long. Wait. Is that 1 unit long? Wait, let me... Tangent t. It should be 1 unit long. Always 1 unit long. Yeah, it literally should be. Yeah. Alright, so this vector is the t hat that we had over here. Now the next thing we know is that t hat here, once you take the derivative with respect to s, with respect to the arc length, we're gonna get kappa, we're gonna get the unit vector times the curvature of that thing. So what I'm gonna do is I'm gonna change this. I'm gonna change this thing a little bit by turning this, by changing the derivative into ds by dt. No, sorry, changing this into dt by ds, and then we have dt by dt, because this is what Desmos will support. It doesn't really support the other kind of, it doesn't support changing it to the arc length. So let's see how we can do that. We have to differentiate this, which is going to be equal to the reciprocal of ds by dt, which is equal to 1 over square root of, okay, yeah, it's going to be equal to 1 over square root of, what's it? The absolute value of the velocity vector. All right. Yeah, I think that works. So therefore, therefore we can we now know that kappa n, which is the normal vector, the rate of change of the tangent vector is going to be equal to 1 over absolute r prime t times dt by dt is equal to that. So now we can write this, we can now draw this into Desmos.com. So now I can define that, can I use kappa here? No, I can't. I do not have Desmodder installed. Desmodder for RPGX. Let me install it real quick. Desmodder installation. How do I install it for RPGX again? Please. All right. Let me see. Mod, is that it? I don't think it's in here. I think it's in the extensions. No kappa. Yeah. Unfortunately, there's no kappa. Ah, there it is. Extensions. It should be here, I think. My extension. Is that all? Okay, I'm gonna go get more extensions. I want Desmodder. Come on. Sir. Desmodder. Desmos unlocked, really? That doesn't exist? Do I? Total number of ratings 2. I'm not quite sure about this. You know what? I'll pass. I'll do it later. I'll try and install it myself later on then. We'll be stuck without. Already exists Chrome Store, right? Yeah, but it apparently doesn't exist on here for some reason. Anyway, if we differentiate the tangent vector here, we are gonna get. We should be. If we differentiate this guy over here, we should be getting the normal vector. So over here, it's the size 1. Hold on. It's the size 1. It's not 1, it's almost 1. If I change the value of r, will it change? Will the size change? It does change as well. If I change the value of v, it also changes. So this is promising. All right, so now we this is the differentiate. This is the normal vector times the kappa. So n here, n, which means normal vector, is going to be equal to the tangent vector divided by the change in tangent vector divided by the its size. Because again, what we want to find is we want to find the velocity vector. Wait, actually no, we're not done yet. Because don't forget that this differentiation means it differentiates with respect to t. Therefore, what we have here really is just this one divided by, I mean, it works, I guess. I guess it works, yeah. But it's not really the full picture. The full picture is we're gonna have to change this. N here is correct, all right. N here is correct. But then the next thing we have to do is we have to find kappa. I'm just gonna use k in place of it first. Kappa is equal to t tangent divided by the velocity vector, the size of the velocity vector. Right. And then that's gonna be, and you're gonna have to dot it with nt. And that's going to be our curvature at a certain point. So kt should be equal to kt here should be something. I don't really know what thing, but it should be something. Anyhow, this, I'm going to change this to the normal vector. And as you can see that indeed it is the normal vector. It is perpendicular to the tangent vector. So as we move along here, it just stays perpendicular to the tangent vector always. All right, and kappa t here just happens to be, let me try something real quick. I'm gonna put VC with 0, yeah. And then I'm gonna, if I remember correctly, yeah, okay. If I remember correctly, it's equal to the radius. The curvature is equal to the reciprocal of the radius of curvature. Does that make sense? Yeah. The curvature is the reciprocal of the radius of the curvature, which means what I'm saying is if we have a curve, right? If we have some curve and we want to find the curvature at this point, we want to find the kappa at this point, then what we can do is we can draw a circle that perfectly, just assume that this is perfect, that perfectly like follows this curve, right? What happens here is this radius of curvature here, r, kappa is equal to 1 over r. That is what it means. Yeah, all right. I don't know what else to say about it. So that's what the curvature really means. All right, moving on. So how do we prove that the curvature is described by this whole function? Well, I don't know, honestly. Let's figure it out. Let's figure it out together, guys. This will become d dt, but again, this will become dt by ds, and this is going to be multiplied by dt over the well, you don't really need the absolute value over there. Let me just remove it there real quick. And I drew it on the wrong layer again. Okay, this isn't the norm of the vector. This is supposed to be just the absolute value here. The double absolute value, personally, I kind of just put it to mean like the norm of the vector, the size of the vector. So that's that. All right, and then that's the ds by dt by ds, and this is dt by dt. In this case, this one over here is going to be equal to 1 over the r prime t, which is already part 1 of this thing done. So this method seems to be kind of promising so far. Let's see what's next. What's next here is we have to find this vector. All right, so we have to find the derivative with respect to time of the tangent vector, which previously we had just calculated. What I calculated to be is give me a sec. I need to calculate real quick. I may have a different idea right now, but I'll stick to this one. Oh, you know what? Nah, fuck it. Okay, let's try that again. I have a better idea. Let's prove this using a different approach. Okay, so first of all, considering the following fact. We know that dt streamer is indices of, yeah, I haven't done this question before. So like this is just I'm just winging it. I'm just doing this with no script. Just bawling. Okay, we do know that not that, wait, let me do that again. For the second time. Okay. So what we want to find is kappa. We do know that kappa n is equal to dt by ds. we know this for a fact. Therefore, we also know that n cross t is equal to 1. The cross product means that the two vectors, we're finding the component of the vector that is perpendicular to each other. If they're perfectly perpendicular to each other, you multiply their sizes together. If they are parallel to each other, it becomes 0. If they are perpendicular, you multiply their sizes together. In our case, n here is 1. The size of n here is 1. The size of t here is 1. Therefore, and we also know that the normal vector is always perpendicular to the tangent vector. Therefore, you take the cross product, you're going to get 1. Which means that if you take the cross product between derivative of t with respect to s with the unit vector t, and then you find the size of it. Guess who's watching the stream while driving? Nice. Just don't hit a deer. What we would get is we're gonna get kappa. So we have to find a way to turn this form into this form. Alright, which shouldn't be a problem. I don't think it's gonna be a problem, because of the fact that t here is simply the same as, well, fun fact, there's no deer. Ah, well, good for you. But is there beer though? Okay. Oop. And then divide that by, we don't divide that by anything just yet because I forgot to tell you that t here is, as we had previously done before, is equal to the just the velocity vector divided by the size of the velocity vector. Very human remains, which I don't remember because of how drunk I am. Nice, nice. You can get rid of them by using what was it called? Piranha solution. Yeah. If you combine, let me think. If you combine H2O2, I think it's hydrogen peroxide, combine it with sulfuric acid at a ratio of around, if I remember correctly, around the ratio of 1 to 3, what you're gonna get is you're gonna get the piranha solution. Why do you think it got its name? Where do you think it got its name from? Yeah, if you pour the solution onto some organic material, it no longer becomes material. It just dematerializes. It's just that strong because of, I don't really know why. I just know how to make it. And this is a really fun thing to think about because of how crazy it is. Like, it would probably melt through your finger if you don't have any gloves on. So it's good for removing organic material. Take that as you will. Anyhow, because of that product, we're gonna have our cross product with dt by ds over here. And all of that divided by the length of the velocity vector. Evil Neon FHD. Yeah, I'm his evil twin. Yeah, and then the next thing that we can do is we can transform this t, not yet, we're going to turn this into the we're going to turn dt by ds into the form that we just had prior. That is dt by ds. dt by ds here becomes dt by dt times 1 over norm of r prime. So this one becomes dt by dt divided by the norm of r prime. And then of course you find the norm of the whole thing. And then again we have the norm of r prime over here, down here, where you can now proceed to group them together. And you're gonna have r primed t cross product with dt by dt divided by this guy squared. All right. So that's that. We're close. We're pretty close. You can probably see how this one will turn into this guy later on, but I need to calculate first how to get that. But we also know that t equals to let's take a break from that term because it's getting a little messy and I don't want to copy it all over again. So dt by dt is going to be equal to d by dt of what? Of d by dt of r prime t divided by r prime t, the norm of r prime t. Okay, which as you can see is a bit of a problem because now we're going to have two terms instead of one term that is just r double prime. Fortunately, it won't be a problem because it turns out to be a cross product. So let me do the thing. This will become negative r prime t divided by absolute r prime. I'm gonna omit the t, and then multiplied by the r prime divided by t. But then you also add in the derivative of the top one, and then divided by just one of this guy. Because again, this is from the product rule. You take the derivative of the top term of the first term. No, you take the derivative of the first term, which is 1 over absolute r, 1 over r prime. You take the derivative while keeping the second term intact. And then you take the derivative of the second term, giving us r double prime, while keeping the lower term, while keeping the other term intact. So that's that. So we're gonna end up with this this big ass thing. We're gonna end up with this big ass vector. Fortunately, the first term disappears. Why does it disappear? Because it's a cross product. I'm gonna stop writing the vector and the t, and because I'm getting a little lazy. I don't want to like keep writing it. But basically, what we're gonna have is we're gonna have d by dt of that, and then r primed over r prime squared. And then you add that, and then you add it with r double prime divided by absolute r prime. Now, what's important is the fact that the product of two vectors that are going in the same direction. Hold on, I will draw the vector for this one in this case. Now, what's important here is the fact that the vector product between these two vectors, the cross product between two parallel vectors is 0, meaning that this term combined with this term, r prime crossed with this term, is going to be 0. Therefore, all that remains is going to be r prime cross r double prime divided by r prime cubed. And that is our value of kappa. Yay! And that solves our question here. Show that the curvature of this thing is described by the vector value function and is given like this. Oh boy. Alright. Any question? I think that was pretty elegant. Yeah, we used like a bunch of vector properties, and we ultimately ended up with what the question gave us. Indeed, it is equal to that. So that's fun. Now we move onwards to the next question, which, well, isn't too many. Let me just go ahead and grab that question. We still have a lot of space for this page and this page. I think I can use this page to do the question. Yeah. All right. The orthorhombic system is described by three orthogonal vectors, say these guys. Find the reciprocal vectors for these systems. What if the system is cubic? How would the reciprocal vectors change? Now, of course, the big question here is, what the fuck is a reciprocal vector? Reciprocal vector. The reciprocal lattice vector is basically that. That's the case for reciprocal lattice. But in this case, yeah, the reciprocal vectors are that one. Oh, right! Okay. Jackpot. Alright, so I remember this now. This is actually what you get to learn in general relativity, but you were never really explicitly told of it. So before we get into that though, let me just explain what it means. What this means. Streamer has a eureka moment. Yeah, I do have that a lot in class. My friends are a little concerned for me. Okay, so the orthorhombic system is described by these three orthogonal vectors. This means that, say that, alright. So this means E1 is this. This is E1. E2 goes along here for 2 units. E2 goes here for 2 units. And E3 goes up here for 3 units. So, what the orthorhombic system means is that when we describe a vector, right? When we describe a vector, how would you normally represent it? Well, normally, hold on, my notifications are. All right, physicist memeing. All right. So when we express a vector, normally in Cartesian system, we would express it in terms of Vx and then the x unit vector. And then we have Vy in the y unit vector. And we have Vc in the c unit vector. This is how we normally represent vector in Cartesian coordinates. So the orthorhombic system here, described by three orthogonal vectors, is basically rephrasing this, using the same vector, but instead of using x, y, and z as basis vectors, we are expressing it in terms of E1, E2, and E3. So, for example, in our case, it will become V1, E1, plus V2, E2, plus V3, E3. So, for example, from this system, let's say we have a vector. Let's say we have a vector system that is like, what should it be? Let's say we have a system that's like 10 unit vector in the x direction. We have, and it goes 6 unit vectors in the 6 in the y direction, and then it goes like 9 in the z direction. If you express it in this orthorhombic system, what we have is we can change this to 10E1 plus 3E2 plus 3E3. So as you can see here, the numbers reduce. You can see here that the component along the y-axis, along the second axis, reduces. That is because the basis vector itself is getting bigger. the basis vector itself got bigger. So to counteract this, how much you have to step in the basis vector direction decreases. So these two are the same vector, just represented in different coordinate system, namely this specific orthonormic system. This is actually a very this is actually what you do use very often in general relativity. So instead of writing a v like that, you would write the v is going to be equal to the v mu e mu. How you would normally write vectors is you would instead write in terms of this. So mu here. So what this means basically you're summing over mu. You're summing over mu. And then you have v mu, e mu. This Einstein's summation notation. This here doesn't really, v mu here doesn't mean v to the power of mu, obviously. This means that it's the muth component of v. So it's like over here, up here, I write 1 down here. This is as if writing the number 1 up here instead, or number 2 up here instead. It's like changing the position where the index go. So over here, it would be equal to like the first component of v, in this case v1, and e1, and v2, e2. Again, this does not mean v squared. This means the second component of v. It's almost the same as this one, but like in curved spacetime, it might not be. But like for our case, it is. So this is what it means. Einstein summation notation. What they want us to find is the reciprocal vector for these systems. The reciprocal vector for this system is a vector such that the reciprocal vectors for this system. So the reciprocal vector for E1. Okay, hold on. Reciprocal maybe when indexing gets done in a superscript instead of subscript because I used subscript for another indexing or something. I forgot the video I watched on it. Yeah, basically the reason they put in indexes on top or down there is because of they have to separate contravariant and covariant components. Like over here, E here is the basis vector that is a covariant thing because the index being down implies that it's a covariant vector, whereas the index being upstairs means it's a contravariant thing. I can't really explain it, really. Yeah, you might have to like look into general relativity a little bit more, or until you make like a video like explaining general relativity with Minecraft or something like that. But basically, the reciprocal vector is basically kind of like the reciprocal vector is the 3D version for covariant vectors. No, for contravariant basis. Oh yeah, I remember now. All right. So like E here is a covariant basis. Here is a covariant basis, which means the reciprocal vector for E mu will be denoted the reciprocal vector for E mu will be denoted E mu with a superscript instead. It has a property such that its property is that E mu dotted. Its property is that if you dot E mu here with E nu, so like if we dot mu with nu here, what we should get the Kronecker delta function. No, the Kronecker delta is not a function. It's the Kronecker delta for mu and nu. What this means is the reciprocal vector must be such that if you dot the two vectors together, if they're the same vectors, you're going to get 1. 1 in the case where mu equals to nu. And if they're not equal, if they're different reciprocals, like if we want the reciprocal of E1 dotted with just the basis E2, we're gonna get 0 for mu unequals to nu. So for example, where let's say we have somehow found the reciprocal vector for E1. The reciprocal vector for E1, dotting this with the normal E1, is going to get you just 1. But if you dot it with E2, you're going to get 0. And if you dot it with E3, you're going to get 0 as well. So yeah, that's what the reciprocal vector system means. All right, got it? Nice. So we have to find something that would make this happen. We have to find something that would make this, be true. So first of all, because of this fact, from this fact, we immediately because E1 and E2 dotted with each other, you get equals 0, and E1 dotted with E3 equals 0. We can immediately infer that E1 is perpendicular to E2, and E1 is also perpendicular to E3. This means that there's going to be some vector that you can write that is such that E1 is equal to E2 having cross product with some unknown vector. And we can also know that we can also write this such that it will be equal to some vector having a cross product with E3. Can you take a guess what what's in the question marks? Okay, at least this is the direction. The direction of the vector. Can you take a guess what the question mark is? Obviously, we immediately know that the direction. I'm just gonna change this to like E hat. Because no one uses this notation. It's just me who's using this notation right now. We just came up with it like 5 seconds ago. What does it mean is E hat has to be parallel to something that is crossed with the unit vector E2 and E3. So what is that vector? Well, we immediately know here that E1 must be in the same direction as E2. No, must go instantly in the same direction as E2 crossed with E3. That way, this the reciprocal. No, not E1 there. E1 up here. Okay. This means that therefore E1 okay, hold on. If E1 is parallel to E2 cross E3, immediately we will know that E1 is immediately we immediately know that E1 is perpendicular to E2 and E1 is perpendicular to E3, which immediately satisfies these two conditions. So we can immediately tell that E1, the reciprocal vector for 1, is going to be something. It's going to be some scalar multiplied by the unit vector multiplied by the cross product of E2 and E3. So that's our first. Okay, so that is going to be our first condition being done. All right. So the next condition is such that E1 dotted with the E1 must be equal to 1. So here we can rewrite it such that we can rewrite it in a way that we would know that E1 here dotted with E1 is equal to something times E2 cross product, having cross product with E3 dotted with E1, and it must be equal to 1. Now, how do we make this expression equal to 1? There's only one thing that we don't know about this expression. How do we make this whole expression equal to 1? Well, we just make that this expression equal to, well, we just make this question mark equal to, hold on, give me a sec. We just make this question mark equal to this whole expression. That way it is guaranteed to be equal to 1. Which immediately tells us that E1 is equal to, hold on, which immediately tells us that E1 is equal to E2 cross E3 divided by E2 cross product with E3 dotted with E1. And now we have successfully found the reciprocal vector for E1. Alright, does that make sense? If you plug plug E1 in here, and then if you plug E1 in here and then you try it out, you will realize that this will indeed satisfy the condition of the Kronecker delta. Therefore, we can. Therefore, the next thing we can do is we can generalize this. So we now know that E mu, the reciprocal vector for the mu vector, is going to be equal to hold on, I don't want that actually. I'm gonna use EI instead. EI equals to EJ cross with EK divided by EJ cross EK dotted by EI, like that. Alright, well that's simple enough, I think, and I think that's fairly straightforward. What do you guys think? I think that makes sense. So, from this, we can use the formula and then just spam the hell out of it. So, I, j, k must be sequential, which means if I is 1, j must be 2 and k must be 3. If I is 2, j must be 3, k must be 1. It's a cyclic permutation. And then if I is equal to 3, j must be 1, k must be 2. So it would be like, So it'd be like 1, 2, 3, 1, 2, 3, 1, 2, 3. There's no out of order. There's nothing out of order. Alright, so let's find the reciprocal vector for E1. Well, we already found the formula. Let's just plug in the formula. What is E2 cross E3? E2 cross with E3 is equal to honestly, I can just E2 cross with E3 is equal to E1. What? Wait. It's equal to 6E1. Wait, what? Give me a sec. We have X, Y, C, 0, 0, 0, 0, 3. Yeah, okay, it's correct. So E1 here is equal to 6. Yeah, it's going to be equal to 6 in the E1 direction. Well, in the X direction. And then divided by 6. Yeah, 6 divided by 6x dotted with E1, which is going to be equal to, this down here is going to be 6. Up here is going to be 6, so it's going to be equal to just x. Which means the reciprocal vector for E1 is just 1, 0, 0, which just happens to be equal to normal E1. But it's not going to be, this is not always going to be the case. Let's consider the next case then. That is E2. E2 is equal to E3 cross E1 divided by E3 cross E1 dotted with E2. E3 cross E1, let me take a look. E3 goes there, E1 goes there, E2. So E2. So this one's gonna be in the direction of, this one's gonna be 3E2 by using the right hand rule. I don't really have to like find it the formal way. Again, this is 3E2. No, not 3E2, sorry. This is not 3E2. This is 3Y. And the same applies for down here. This is going to be 3 in the Y hat. This is going to be 3Y hat. And dotted with E2. And we're going to end up with 1 over 2 Y hat. Which is equal to 0, 1/2, 0. And lastly E3. The reciprocal vector for E3 is equal to E1 cross E2 divided by E1 cross E2 dotted by E3. E1 cross E2 is X goes there, Y goes there, so it's going to be in the plus C direction. There's going to be 2C. Then it's also going to be 2C dotted by 2C dotted with the E3 is going to be in the 3C. So all of this will give us 1 over 3 in the C direction. And that is our reciprocal vectors. So that answers this problem. Alright. That was a bit of a lengthy question, mainly because I had to like establish what the reciprocal vectors are first. But it's alright. We just have like one more problem, one more question, which is relatively simple. It's mainly, this isn't even mathematics. This question isn't even mathematics, because this question it's mainly just explaining. It's just explaining why things are. Okay. So first of all, consider a central force problem. If we let this be this, where r denotes the distance from the origin and r hat denotes the unit radial direction, the orbital angular momentum is defined by that guy. The angular momentum is equal to r cross p, which means that let's say if something's orbiting around this, let's say if we have the sun or something, and let's say a planet is orbiting around it. Then that means over here the velocity is going in this direction, and the radial and the vector r is going in this direction. All right. So if L is the angular momentum, that means L must point in the direction perpendicular to both of these guys by using the by using the right-hand rule. If you use the right-hand rule, in this case, the angular momentum is going to be pointing upwards. So if this object is orbiting around the sun like this, then the angular velocity, the angular momentum vector is going to point in the direction that is in the axis that is in the direction that is the axis of rotation. So if you look from a top-down view, right? You look from a top-down view, right? V goes up there, R goes here. Therefore, the the L is going to be coming out of the paper. Okay, and that's the definition of the angular momentum. All right. Now let's prove that L is constant when the force is central. When the force is central, let's prove that L is constant by just differentiating it. If we differentiate it and it ends up being 0, then we can confirm that it is a constant independent of time. So if we do that, we're going to have R cross F plus V cross P. Can you see where this come from? You see where this came from. If we take the if we differentiate this function, right? We have is a cross product. We differentiate the first term. No, we differentiate the second term, keeping the first term intact. The change in momentum over time is simply the force. Then we differentiate the first term, leaving the second term intact. And the rate of change in position vector is just the velocity vector. All right. And according to the given, hold on, this should be capital F. And according to the given case of the problem, the vector F here is f of r in the r direction. So this becomes f of r unit vector r, and this is equal to v cross mv. Now here you can clearly see that this term is 0 because this r here points in the radial direction r hat, and this one is also pointing in the radial direction r hat. Therefore, if you cross two vectors that are pointing in the same direction, what you're going to get is you're going to get the 0 vector. The same also applies to this right-hand side. V here is pointing in the same direction as V. Therefore, we can say that it is going to result in a 0 vector. Therefore, dl by dt is 0, which means that the angular velocity, the angular momentum of the system is going to be constant. That is, in this system, angular momentum is conserved. Next up, explain why the object experiencing such central force must orbit. No way you're being a mad scientist live on set. Hello, Slasher. Welcome to the stream. Yep, I've been doing this for like 7 streams now. Yeah, I've been doing this for 7 streams now. Had a lot of fun, but wasted quite a bit of time. But yeah, it's still fun though. I'm getting views, so that's what really matters. So explain why the object experiencing such a central force must be on a fixed plane. This is what it is saying is that once you're spinning around on this plane, right? It doesn't just randomly just change over. It doesn't just randomly tilt over. In this case, well, if you have something that pushes it, then obviously it will start to tilt around. But in this case, it won't because of the fact that the angular momentum is always perpendicular. The angular velocity is perpendicular to the plane of orbit. Is perpendicular to the plane of orbit, which means if it suddenly changes to a different plane of orbit, it means that the angular velocity is changing. And if the angular velocity is changing, it means that angular momentum is not conserved. Okay, sorry. If the angular momentum is changing, that means the angular momentum is not conserved. And if the angular momentum is not conserved, it means that, well, it doesn't line up with what we were given in the question. Therefore, this object that is experiencing this force, central force, is going to orbit on a fixed plane. That is, the plane is fixed. It's not shifting. It's not random. If it orbits around this plane, it's not going to randomly tilt up. It's not going to randomly tilt down or anything like that. The plane is going to be fixed. This is because of conservation of angular momentum. All right, and that is our my homework. And yeah, it's a good time for me to go have my dinner. So thank you for watching. I'll be back to playing Silk Song. Wait, shit, I do have another homework that I have to do. Well, never mind then. Silk Song can wait for a few more hours. Yeah. So yeah, that's it. First question. And well, for today's homework entirely, in fact. So if you guys want to like look at all the questions, just the VOD will always be up. As long as like YouTube doesn't delete VODs. I'm pretty sure YouTube just doesn't delete VODs anyway. So like I'm just gonna scroll through this at the end so that when you guys wanna like come and take a look at the solutions yourself. This one as well. If you guys wanna like catch up on the stream for later on. And we have this one vector, this one problems about vectors. And yeah, that's it. So, thank you for watching. Thank you for tuning in. Yeah, I got nothing else. So, have a great day or night. And I'll see you next stream or next video if I do somehow manage to get the video up before the stream. Well, anyway, thank you for watching. See you guys next time. Bye.